When a jet executes a dynamic maneuver, it is subjected to intense physical forces. Thrust, drag, lift, and weight act upon the airframe simultaneously. The standard method of teaching vectors represents these forces as an array of three numbers along an x, y, and z axes. This reveals a disconnect. The universe does not possess a predefined Cartesian grid. While a coordinate system might rotate or shift wildly around the aircraft, the physical arrows of thrust and lift remain fixed. The numerical values change, but the physics does not. Physical laws must hold true regardless of the coordinate system we choose to overlay. To master dynamics, we must decouple the vector from its local coordinates. We begin by identifying quantities that are independent of direction. Mass, pressure, and volume are scalar quantities, defined entirely by a single number. Vector quantities, such as aerodynamic thrust or orbital velocity, require a specific direction to exist. Precise terminology is required here. Speed is a scalar magnitude, while velocity is a vector. Mass is the scalar matter, but weight is vector force. Vectors function as geometric objects, encoding the directional truth of the physical world. A vector's identity depends only on its magnitude and direction. If we take two vectors and slide them across the screen to overlap, we find they are the exact same geometric object, regardless of where they started. The choice of origin is mathematically arbitrary. Orbital mechanics provides the ultimate proof of this origin independence. While both planets orbit the Sun, we shift our origin to the Earth. By subtracting Earth's position vector from the Mars vector, we find Mars's relative position. From Earth's perspective, this vector traces a looping pattern called an epicycle. Whether we calculate the positions from the Sun or the Earth, the underlying spatial displacement between the planets remains identical. Vector multiplication decodes the geometry of space through two distinct operations. The scalar product, or dot product, acts as a tool for projection. It drops a perpendicular line from one vector to another, isolating the component that points along a specific line. The vector product, or cross product, defines an oriented area. When one vector sweeps across another, it generates a shaded parallelogram. We assign a direction to this area using the right-hand screw rule. A new vector extrudes perfectly perpendicular to the plane of the area. In 3 dimensions, specifying the size and orientation of a plane requires exactly 3 numbers. Because a standard 3D vector also contains 3 numbers, we can package a 2-dimensional surface into a single 3-dimensional arrow. This is a mathematical anomaly unique to 3D space. These geometric operations govern rotation. We map a position vector r to a rotating body and an angular velocity vector omega along its axis. Their cross product generates the tangential velocity, perfectly tracing the point's circular path. Torque operates through the same geometric logic. By taking the cross product of a position vector and a force vector, we determine the change in angular momentum. And these physical truths function perfectly in our models without ever referencing an x, y, or z axis. While vectors are geometrically absolute, calculating physical outcomes requires us to plug in components. Standard Cartesian notation is inefficient. Evaluating a dot product requires writing out every component manually, creating algebraic clutter that worsens in higher dimensions. Suffix notation replaces this clutter. Using a generalized index, I, we represent infinite dimensions in a single compact term. Utilizing orthonormal basis vectors allows equations to scale without breaking down into manual bookkeeping. To manage these indices, we use the Kronecker delta. The delta's rules are binary: 1 if indices match, 0 if they differ. This creates a sifting property. In complex summations, the delta eliminates misaligned terms. It acts like a virus, seeking an index, collapsing the summation, and replacing it with its own. This powerful mechanism allows us to evaluate massive systems of physical equations by instantly zeroing out invalid cross-terms. General relativity required taking this notation to its absolute limit to handle the complexities of curved spacetime. Einstein simplified the process with a single convention. If a suffix appears twice in a term, a summation across all dimensions is automatically implied. The summation signs fade away, leaving a hypercompressed and elegant format. This convention ensures dimensional accuracy and balances equations automatically, relying on the structure of the math rather than manual oversight. We master index notation and arbitrary coordinates to transcend them. This allows us to translate the geometric reality of the universe into an algebra powerful enough to map it.